All right, everyone, we are back, and today we are going to talk about what we left off with last time, which is the atomistic basis of linear elasticity on Young's modulus. So we've learned a lot about Young's modulus, stress at failure, but these are not just things that you can find on a stress-strain curve. They have real values that, at their origin, are atomistic in nature, particularly the Young's modulus, because, again, you're in that linear elastic regime where you're literally just pulling on bonds. And we know that the energy, Lj, of these bonds is governed by potentials, not just Leonard-Jones potentials, but other potentials. So really, the stiffness of these bonds can be determined by this potential, because we know we can't actually relate any potential or distribution, and the width of that distribution here, the curvature, we'll see that in a second, is basically going to, the width of distribution will be related to essentially the stiffness of the potential. If you're interested in this, there's actually a very, very interesting phenomenon with quantum harmonic oscillators and relating essentially the stiffness of the width or the standard deviation of distribution to the stiffness of the trap. But again, that's just very, very bad self-promotion on a paper that is very, very may not be interesting to read. But anyways, but we are going to relate essentially bonding, chemical bonding, to how weak, or actually not how weak, excuse me, but how compliant or how stiff something is. Again, this is something that we can't do in the plasticity regime, only in the elastic regime. Because in plasticity, as we're going to see, there's lots of inhomogeneities, defects, dislocations, and then very, very, very soon, right after this lecture, we're going to see that for some materials, stiffness is actually derived from entropic considerations. But we're getting a little bit ahead of ourselves. Let's go back, and we kind of already mentioned this internal energy U. So let's approach it from a thermodynamic perspective and see, and basically just look at a system under uniaxial tension in the one direction. So we're stretching the bonds, and that is going to change the internal energy of our system. So going back from our kind of brief overview of thermodynamics, isn't it so good that we did that? We're going to change the internal energy of our system U, and that is going to be combined from a work term and basically a heat term. So as hopefully you've seen before. So we're taking our system here, as you can see as well here, we're applying a uniaxial tension in the 1-1 direction. We're going to take our system from system 1 to system 2. So going from system 1 to system 2, our change in our internal energy of our system is larger. So this is something the system doesn't want to do. We're stretching our bonds, we're pulling them further apart. We're going to increase the internal energy of our system, and thus we are doing work on our system. And we know if there's a change in work, what is our work general form? Force times some displacement, delta x. So this, if you remember, this is our force. Our delta x, if we remember epsilon 1, it is going to be basically my new delta. Basically, it's going to be the change in delta. Change in the one direction divided by delta one direction. So if I want to rewrite that, it's just going to be dE times this. And we can see here that our work term, this term here, that's a volume. So stress times a strain times a volume, that's going to give us our work term. And you could check out those units. So remember, stress is Newton per meter squared. If I try to multiply that by a meter cubed, the volume, Newton meter, joules, everyone, we're good to go. So we've kind of seen that before from thermodynamics. I know my dq, second law of thermodynamics, is equal to TdS. So our system becomes, internal energy is going to change as a function of the change, that strain in my system, plus some entropic term. Or I could rearrange this whole equation in terms of stress, where my stress is going to be proportional to the change in my internal energy of our system as a function of my change of strain, and the change in my entropy of my system as I change the strain, or as I strain the system. So this is very, very critically important. For most crystalline materials, metals, ceramics, amorphous materials, probably some glass materials that are well below Tg, so polymers that are below Tg, this value of dsDE, or d epsilon, is going to be very, very, very small, to the point where it is negligible. So we can basically cancel that out right here, right now. So for polymers that are above Tg, for rubbers or elastomers, this term is very significant, and actually it's going to dominate essentially the system behavior. So don't worry about that. Rubber elasticity is coming right after this lecture. So Yeah, it's going to come soon, and then soon you're not going to like it, but then you're going to really like it, because that's how we essentially do things in this course. So we can go back to this right now, and we see that for crystalline materials, we can redefine this system. If we're looking at the atomic level, I can look at the atomic volume, or essentially your kind of basically the atomic spacing. So we could just replace this volume term here with our capital sigma, this term here, and we have it. And again, what was the whole point? We wanted to kind of derive terms in terms of an energy of our system. So our Young's modulus is just the slope of our stress strain curve. So you take another partial derivative, and we see that our Young's modulus is proportional to the second derivative of our internal energy with respect to strain. So this is not a fully, kind of fleshed out functional form yet, right? Because we don't have an expression where U is, where our internal energy scales as a function of our strain. We do have potential energy terms, U, in terms of R. So what we have to do, what we have to look at, we want to rewrite our strain terms in terms of R, where R is just our new radius. Basically, this is, again, our distance, R here. This R naught is our equilibrium distance, which is always 2R. It's our equilibrium distance in the system if it's a metal and ceramic and other materials. So this is great. Again, we can now actually look we could do some, let's kind of rewrite our expression. So we know this is true. We also know that, again, stress is equal to force over unit area. So this area, A naught, is equal to, again, if I have a cubic system, R naught squared. So if I'm pulling essentially my cube like this. So if I'm pulling here, any normal stress, it's a cube. My cube side length is R naught, so it's just going to be over R naught squared. So I could rewrite my expression like this. If I take the derivative of this with respect to R, I'm going to get 1 over R naught. Again, this just kind of falls from here, and this equation derives from here. And now I can start to rewrite essentially my functions here. And this should be not a partial, this should be a dE. But I can rewrite my expression. And we can see that, actually, we can see that right here. So I can rewrite these terms. Let's just rewrite it here. You can see E, I can just do my, basically, little chain rule kind of thing. So d theta dr, d epsilon, and then get those canceled out. And now I'm left with this expression right here. So my Young's modulus is proportional to 1 over R naught du dr squared. Well, how do we arrive at this result? So let's break this down here. So first we have d sigma dr. So again, let's break this down effectively. So what does this mean? We already have d theta is df over R naught squared. And then we're taking basically d dr of this. And we know that basically we could relate force to the negative gradient of a potential. But why don't we see a negative here? Well, this is the force between the atoms, but we're pulling. So this just is describing the force between these two atoms, but we're pulling on it. So the force that we're actually exerting here, this little df, is in the opposite direction. So that's going to be a plus. So if I do the partial derivative of this, of f, which is already equal to minus the gradient of that, that's going to leave me with del squared u dr squared, because again, derivative, times 1 over R naught squared. What about dr d eta? Well, if we remove this around, you'll see that that'll result in an R naught, hence why we have 1 over R naught here. Beautiful description. But again, the key thing, this second derivative is evaluated at R equals R naught. Evaluated at R equals R naught equals 2R. So be careful there. You can also arrive at this with our elastic strain energy basic expression below. You'll see that a lot in mechanics and a lot in this class, that arriving at the same expression from two different methodologies is a really good way to kind of know that you're correct. So we can relate this again to the internal energy of our system. Again, still using this relationship here, and we could use our good old friend, the chain rule. So here, break it apart. So we have, again, our internal energy expression, which is what we want. dr d eta, so you can kind of see this right here. What is that going to leave us with? It's going to leave us with this r naught squared. Great. So that's this is essentially this expression right here. What about here? dr with respect to d eta second derivative. Well, second derivative, that'll be equal to 0, so that disappears. So with this expression, this is a little bit different from the previous one. But again, we want, actually I think there's an error here. This should be squared. I'll make sure to make that change. We also know here, again, this is r naught squared. We want to basically, this is our energy. Again, our atomic volume is equal to this, again, as long as we're a cubic system. Our strain energy per unit volume will basically just be the energy per atom divided by the volume. So the energy per atom is going to be Z is the number of nearest neighbors over 2. So that's going to be our ESE. So our USE term is just the energy of the atom at some distance r minus the atom at, basically it's at distance here, divided by the volume. So basically, because it's this ESE, we need to divide out by the volume. And when you divide out by the volume, you're left with, what do you know? Looks very similar to our other term, right? This is just a little bit more complete because we're kind of explicitly taking into account the energy per atom here, but it's not going to affect it too much. So this is very important in embedded atom potentials. Again, very different if we know the values. It could be your potentials get much more complex. But this is our expression, and what does this tell us? Again, it's telling us that our Young's modulus, our stiffness, is proportional to second derivative of u dr squared, which is the curvature. It's basically the stiffness, or the amount of curvature. If our well is like this, that is a more compliant material. If it's very stiff, if we don't have a large, if you flip, whenever you have an energy potential, you could flip it, and that's going to be your probability distribution. So if this is my energy, this is my probability per r. My stiffness is basically my standard deviation here. So the width of the well, not the width of the well, but basically the curvature of the well, that's going to give you that material property. So amazing, right? Force is basically proportional to basically our du dr. So force is from this. We can take the derivative of this, set it equal to 0, and we'll find r is equal to r naught, our equilibrium distance. So those potentials tell you equilibrium distance. It tells you where force is maximized. It can also tell you about your Young's modulus too. So everything is in your potential information. You all have great potential. So next time we are going to, excuse the pun, we're going to get into our thermal expansion coefficient and how that affects materials as well. All right, thanks. See you in the next video.